is the most important thing in case of precipitation, is a high degree of concentration of radionuclide or any element. It's quite high, simple, and convenient from point of view of practice work. And also sometimes it can be scaled up from milligrams to kilograms or high concentration of your solutions. But in case of use it in some kind of technologies, there are some problems in general. About problems of precipitation. First time, I think many of you make precipitation in your labs, and you know that if you want to filter all the precipitate, you need a lot of time. Yes, as I already say, when we talking about high-scale technologies, chemical and radiochemical technologies, there are really some problems for make precipitation with high amounts of solutions. Also, there's maybe problems when we use large amounts of carrier, because you after you make precipitate, your solution with carrier is also can be considered as a radioactive waste, and very often it's more usual situation that in case of precipitation, this precipitate can be contaminated with different radionuclides, and so using precipitation for some selective processes is not recommended. Next type is solvent extraction, or English literature you can find liquid extraction, sometimes just liquid extraction. Why it's important? Because in English language, extraction it's a quite general word. For example, when we're talking about oil, when we gain it, it's called oil extraction. So why it's important when we talk about chemistry, say solvent extraction or liquid extraction. These techniques widely used in lab in case of analytical chemistry, organic chemistry, and biochemistry, and also in food technologies, biotechnologies, and hydrometallurgy. In general, most radiochemical technology is just a branch of hydrometallurgy techniques. So what's going on? We have two immiscible liquids. One of them is oil solvent, organic solvent. In many times it's non-polar, and as second phase is usually used water solution with really different components in it. And of course, sometimes we have something that have sometimes oil part is have higher density, sometimes less density, and based on it, where if organic phase has higher density, is go to the bottom of tube, or it's go to the high part of the tube. So in general, if you want to have if we want to understand what is solvent extraction, so it's a redistribution of a component between two immiscible liquids. It works in this way. We have two liquids. For example, in the beginning of this process, we have some components. It's marked with letter A here. After that, we make the contact of phases. In case of lab, you need to shake your sample with very high rate. And after that, there is separation of phases. Mostly it goes just by gravity. And after that, we can separate these phases and we concentrate our component in organic phases. Of course, there is some nomenclature. In case, I think it's more used in case of technologies. This solution is called feed solution, initial solution. This one is organic phase. It can be composed from extractant, if extractant is liquid, or we use for solid extractants some kind of diluent or solvent to dissolve it in organic. After the process, organic phase is called extract, and the aqueous phase is raffinate. And of course, after And of course, it's more familiar for us to use aqueous solution. After extraction, we need to make back extraction to remove components from organic phase back to the aqueous phase. Of course, all of these procedures that I show there, I think they're boring because as it's right here is just going component from one phase to another phase, and here case of separation of radionuclides is in solvent extraction. It's very spread that in first stage we extract both components A and B, and after that we make selective scrubbing. We use aqueous solution in which we can remove only one component from organic phase. And what is the chemistry behind solvent extraction? I think the main and important part is the mechanism of solvent extraction. Based on different literature, there are some kind of different classification. Here we can, I will show maybe the most common classification of mechanism. And first one is a physical redistribution. Sometimes we work solution of compounds that in real have low solubility in aqueous phase. For example, here you can see solvent extraction of iodine from water, where there's a low solubility of iodine, in the toluene, where iodine have high solubility, and also you can see such purple color after extraction. And so it works when we have non-polar compounds with molecule structure in water. For example, it can be weakly polar organic molecules, some kind of halogens, and some kind of molecules with high symmetry. And also by this mechanism, there can be opposite process when molecules of water can transfer into the organic phase. And also extractant, we will see extractants later, can go to the aqueous phase from organic. And if you want to write a chemical equation, it's useful when we're talking about chemistry. This equation looks like very simple. And let's go on to more complex system. I think this mechanism is the most spread in all the extractants, the solvent mechanism. Driving force of it is a formation of organosoluble complexes. And if you want to understand if our molecule can act as an extractant, we should find in it electron donor atoms. Here are they. And it should be a natural compounds that can be solved in some kind of organic phases. By this mechanism, in general, we can extract salts of metals and acids, and also general equation for it. You can find it here. So we have cation of metal in an aqueous phase. Of course, we have some counter ions for this metal cation, and also an aqueous phase. And in the organic phase, there's a ligand. And after that, this complex is formed in organic solution. So we mark it as organic. Sometimes there are bright description, the components that in organic phase, we use this dash to understand what's organic, what is aqueous phase. There's some, I think, a little bit different kind of this mechanism when we can prove that molecules of water also go through this kind of complex. I think in general the idea is the same, but sometimes it's really important what the activity of water you have in your starting solution. By this mechanism, we can extract complex acids, for example, acids of this group of elements. Sometimes they called like metalloids because they properties between metals and non-metals in periodic table, and also some kind of metals that in aqueous solution are presented as anions, for example, perrhenate anion, precipitate anion, and so on. And as I say, in case of equation, there's some difference connected with water molecules that they take place in the equation, and we can find them in the organic soluble complex. And there are some typical extractants. Here you can see TBP, tributyl phosphate. I think it's the most spread organic molecule in radiochemistry because Purix process for isolation of uranium and plutonium from spent nuclear fuel is based on this extractant. Also, another kind of phosphor-containing organic molecules is phosphine oxides. Here you can see 3-octyl phosphine oxide, but in industrial scale, it's often used the phosphine oxide with different substitutes here. Another molecule that was producer of TBP is methyl-isobutyl ketone. And also sometimes triethylamine can act as an extractant that works in by solvent mechanism of extraction. Also, if you want more organic compounds, there are interesting class of compounds, crown ethers and calixarenes. Their main feature that they can selective bind different metals of first or second group of periodic table based on the size of the cavity. They, for example, if you use this kind of crown ether, it can bind lithium cation. If you go to more, we can bind sodium, potassium, and so on. Also, there are some microcycles with possibilities of different synthetic modification that can make fine tuning for different cations for their selective extraction into organic phase. So another big mechanism, big class of extractants is a cation exchange mechanism. So the main idea here is the formation of organosoluble salt, and in case of this mechanism, extractant is organosoluble acid. Here you can see structure formula of main common extractants. It is phosphoric, phosphonic, and phosphinic acid, and in rare cases it can be carboxylic acids. And by this mechanism, we can extract metal cations and also sometimes metal salts. The mechanism is more difficult than in case of solvate mechanism. Why it's so? First, a feature here that these molecules, they have, we can imagine them. They have two parts. One is more hydrophobic, another one is less hydrophobic, and we put them into non-polar media in organic solution. There's some connection by hydrogen bonds between hydrophilic parts of these molecules, and because of it, these extractants are present in the organic phase like dimers of acids. And we should take it into the account when we write an equation for this process. And also, this dimerization have influence on composition of organic soluble complex. It looks like quite difficult. Also, because we have cation exchange, a cation of metal goes to the organic phase, and for equation of the charge, number of protons should go from organic phase into water phase, and because of it, we obtained increasing of concentration of protons in the water phase, so pH will be lower than in the beginning. And there are some examples of extractants that works on this mechanism. For example, it's D2-ethyl phosphoric acid. It has, I think, about 10 abbreviations. Here I show only 2 of them. Another one of extractants that used even in industrial scale. It's very, it looks like very similar with HDHP, but you can see that there is a bond between phosphorus and carbon here. And also, as I say, family of carboxylic acids, but their composition can be different. There are different substituents in this position. But when we have some kind of mixture of compounds, we can easily obtain for industrial scale uses. And I think the last mechanism is an ion exchange mechanism. So the same idea. There's a formation of organosoluble salt and exchange of ions going on. But here, extractant should contain the organic cation. First, very wide classes that use for isolation of radionuclides by this mechanism is a quantitative ammonium basis. Here are they. And every time when we obtain stable cation in organic phase, this can act as an extractant. So also you can see the equation for this mechanism. By this equation, of course, we can extract only anions. For example, anions of metals that are presented in aqueous phase as anions with high oxidation states as technetium, and anionic complex of different cations if they can form these ionic cations. And also during solvent extraction, there are some kind of problems, and one of the main problems is a problem of phase stability. Solvent extraction works well when we have only two phases in the beginning and the end. But sometimes, for example, if you shake our sample in very high rate, you get the emulsion. So you two liquids make a stable emulsion, and it's difficult to separate it. You need to use, for example, centrifugation, but sometimes also it also couldn't help. And there are some, of course, there are some parameters, some values that we use to describe solvent extraction features. I think here the most important, this one. So distribution coefficient, it marks with KD, OD. This is very simple parameter. It's we can calculate it by if we divide concentration in organic phase of our compound in organic phase by this compound in aqueous phase. When this parameter is higher than 1, it means that our compound goes most in organic phase. If is it lower than 1, it remains in the aqueous phase. Also, if we're talking about separation of radionuclides, we use this separation factor that also calculate as division of two distribution ratios for two components. There is no separation if it equals to 1, and we need to, in general, we need to obtain the higher separation factor. Is it possible? Also, if we want to highlight what part of element goes to the organic phase, we can calculate extraction rate. The calculation is simple. We divide concentration organic phase into the concentration of component in initial state. Also, it is easy to show that it can be calculated like in this formula that based on distribution ratio. Also, when we're talking about very concentrated solution, it's important what's the highest amount of element that organic phase can extract. So it's called extractant capacity. And also there's some general rules. What is the most convenient condition for separation of two elements? They can write in this way, but this look like some ideal situation, and in most cases there is difficult to find them. What can affect the solvent extraction? What can be in initial aqueous solution that will have an effect on the distribution ratio or on the capacity of solvent extraction. This is called Salting-Cow effect, Salting-Cow agent. So we called Salting-Cow agent some unextractable salt that have the same anion of that extracted compound. And you here can see that is some kind of solvent extraction isotherms. Here you can see the concentration in organic phase. Here you can see concentration in aqueous phase. And this is isotherm when we haven't any sodium nitrate in aqueous phase. And if we go to the 4 mole per liter sodium nitrate, you can easily see that this isotherm becomes with a higher slope here. What it means? It means that we can saturate our organic phase, even have about 40 grams per liter of uranium in aqueous phase. And when we have no Salting-Cow agent, it's we obtain saturation only if we have such amount of uranium in initial aqueous phase. Why it's happening? There are two driving forces of Salting-Cow. First one is looks like a shift of chemical equilibrium. We makes more concentration of anions in the initial solution. As we know, anions go to the complex, and because of it, we shift our equilibrium towards the formation of complex compound. And also another thing, in general, all of cations in aqueous solutions, they are presented as aqueous complexes. And first part of solvent extraction is devoted to that molecules of water go from these cations, and extractant can bind them. And if we will lower the activity of these molecules, their solvent extraction will go easier. And also another important thing is the effect of acidity. Here you can see the dependence of distribution ratio, or even its logarithmic value. From here, this is pH, and here this is mole per liters for nitric acid. And there are some maxima, some minima. And why it's happened? When we use very low acidic solutions, for example, when pH is 4.5, there is no extraction at all, because molybdenum is presented in hydrolysis species. They looks like here. After that, after pH goes lower, or concentration of acidity goes higher, of acid, so this the hydrolytic form goes to the cationic form, and here we can see solvent extraction. But then we observed protonation of extractant, and because of it, distribution ratios go lower. And when we go to the high concentrated solutions of nitric acid, we can obtain change of solvent extraction mechanism. Here is a cation exchange, and here we can see solvate mechanism of solvent extraction. So in case of solvent extraction, its pros. First of all, because there's a wide series of extractants, we can find extractants that can have selectivity or even specifically bind our cation that we want to remove from aqueous solution. This technique is widely used in technological scale, not only in case of radiochemistry, but also in case of hydrometallurgy. It's a part of chemical technologies that are used for isolation of different metals from solution of ores. Also, very often, in case of micro quantity of radionuclides, there is no dependence of distribution ratios or Percheron coefficients on the concentration of radionuclides, and also it's easily to make back extraction into aqueous phase from organic phase. But of course, some cons. First of all, the bigger part of organic phase is some kind of organic diluent. Most of them are toxic or flammable substances. Sometimes when we cannot obtain selective extractant, we need to make lots of extraction, multiple extraction might be required. But also I can add here that in case of technological scale, it's an easy task. Also, because we use organic, sometimes we obtain large volumes of organic wastes. It's also dangerous, even it has no radionuclides in it. It's still toxic chemical compounds. And sometimes also we can have the problem with the purity of initial solvent. Some impurities can dramatically change solvent extraction process. And the last one, but not the least technique, is the chromatography. As I already said, this technique is really widely used in all branches of chemistry. It's really difficult to imagine some kind of chemistry, wet chemistry, for example, where there is no chromatography. So how it works? Let's go to this figure. So if we try to make this process on basis of extraction, here we also have a distribution, but now phases is stationary and mobile. Stationary phase is a solid phase, mobile phase is liquid phase, and here presentation static mode, when we just have the same contact of phases like in solid extraction, we have distribution, okay? But in case of chromatography, it's very easy to make dynamic processes. For example, if you put in test tube the chromatography resin, just by illusion of mobile phase by solid phase, we have multiply times static process. In solvent extraction, we're talking about just one contact of phases. Here we can obtain dozens of contacts just using very simple chemical equipment. Yes, this is called a stereotic plate. Is a layer when there is one equilibrium occurs. And go back. Because most part of radionuclides is anions, mostly is cations, because the biggest part of periodic table is the metals. Here we use ion exchange chromatography. It's based on electrostatic attraction, and in most part we obtain reversible exchange of cations, and of course divided by charges. There's a cation exchange and ion exchange chromatography. Next. Also, if we want to try to imagine this process, there's some GIF. The first blue dots are the component that has lower affinity towards resin, and red have affinity a little bit higher. This is just an example, because in general nobody uses chromatography in this practical way. And here we can see the concentration profile of components that go from this column. So methods, here we can see frontal methods of chromatography. We just put solution with no pause and obtained two fraction of components. But in general, we can be a displacement technique and eluent technique is used. Both in these cases, we put all of the anions on the column, and after that we make something like scrubbing. We make some conditions that give us opportunity to remove one cation on one type of cations, and another one is still in the column. In case of displacement, it works when we take cation that has the highest affinity towards solvent, and it push away all cations that was in this column, and there's some kind of Ceria in what they go from the column. And the most spread technique is the eluent mode of chromatography, when we put in the column a solution that have special acidity, special components that will remove only cations of interest for us. How stationary fires look like? So we have inert support. It looks like some to the frame, and we add into the support some kind of functional groups that give us ion exchange. So support is made from polymer. For example, this is a copolymer of styrene and divinylbenzene. Divinylbenzene here is used to make 3D substance from 2D linears of styrene. And after that, by some chemical processes, we put some functional groups on it. And if we try to imagine how it looks like in microscale, it looks like in this way. So not all functional groups are on the surface. Some of them in the inner part of this resin. It's important because very often you need a time for components go to the inner part of their inner support for have some interaction with the functional groups in it. Functional group for cation exchange, sulfonate group, I think the most popular. In Russian, there is sorbent that called Q2. For Russian, it's cationic universal cationic resin, because it works in a really different pH, because sulfuric acid is a strong acid, and this group is dissipated in really different conditions. And in case for anion exchange, as we already see, quaternary amine or bases on it can be used for as a functional group for anion exchange. And this picture, I believe you have seen different resins for many times. And also some kind of mathematical presentation of parameters. One is distribution coefficient. It looks like very similar for distribution ratio in case of solvent extraction, and the same as a separation factor that also calculated as division of KDs. Here just one feature about that we should take into account the volume of aqueous phase and mass of solid sorbent that we use to estimate this coefficient. So some pros of ion exchange. It's quite simple because it's chromatography. It's quite simple and effective. So really wide range of applications from lab to technological scale. Very often we can obtain high chemical recovery, and there's some good separation in case of counter ions that can destroy the separation. And cons. Also, there's a problem of secondary waste. Another problem that for sometimes we can use resins based on sulfuric acid, and we need to use some kind of carboxylic acid based resin. and there are some, and it will be problem with pH control. And when we try to compare selectivity, for example, with solvent extraction has high selectivity in comparison with chromatography, ion exchange chromatography. And there is some combination of these two techniques. It's called extraction chromatography, where we use as functional groups extractants or ligands that use in solvent extraction. So, as we told, efficiency of chromatography based on that this is a dynamic process. We can easily realize dynamic process in lab scale. In case of solvent extraction, you use a special machine to make counter-current process, and it's useful only in technological scale. But chromatography, one more time, can be easily used in lab. But it has low selectivity. As we say, extractants can be we can find the extractants that has high selectivity towards cations that we want to remove. And if we combine these techniques, we obtain extraction chromatography that has efficiency of chromatography and selectivity of ligands that we use. It's nice because in case when we try to find good conditions for separation, convenient separation for separation, we can just see through the solvent extraction properties of ligands, and these properties will be close to properties of extraction chromatography resin that is based on this extractant. So also there is the same idea. We have inert support. There's of course some requirements for materials that we use like inert support. So it should be inert in respect to organic phase extractant elements that we going to separate. For mobile phase that we use, you understand that sometimes, for example, we need to use really high acidic solutions, or in contrast, solution with very high amount of bases. Also, it should be stable when we're talking about some mechanical actions with resins. It is very preferable if it has high specific surface, but from other hand, there it should be defined pore size distribution. The particles of resin should be spherical, and mainly some for these purposes, polymers and rarely silicates are used. Well, in case of organic phase that we put on this inert support, it should be liquid. The best way that we use pure liquid extractant, but of course, in many cases, we should use dissolved extractant. The viscosity of this organic phase should be proper to put this organic phase on the inert support. Of course, we want high selectivity. We also need that chemical, physical, mechanical stable extractant was on this surface, and the capacity, so like looks like a capacity of organic phase in solvent extraction also should be high as possible. So this is some figures. I believe Ramis Aliyev, he also have a lecture about practical aspects of using of this technique. He will talk to you more about practical parts of this. Let's go on. So there's some examples of resins that used for certain purposes. For example, for actinide removal, this is Teva resin. It's called for tetravalent actinides. U-Teva resin is abbreviation for uranium and tetravalent actinides. Strontium resin that based on a crown ester that is suitable by size for strontium cation, and sometimes this cation is used for this ligand is used for isolation of strontium. Here you can see that when we compare it with elements of metals of first and the second group periodic table, it really has very good selectivity even in presence of first group. and that more important, even in presence of cations of second group, even that is lower in the ionic radii compared to the strontium, and in case when it's higher. So it in phases that this ligand works by size control binding. And also some pros and cons of extraction chromatography. Here you can see very, I think, ambitious phrase that the state-of-the-art method. I think this method is known for 20 years, but of course it's really selective, really express in case of some lab experiments. We can also combine, and I think you will see, individual columns for different radionuclides. We can make some kind of a big column from number of columns and obtain different radionuclides in one of the column. As I already said, high selective, high productivity, but cons, this is expensive method. The sorbents, the resins can have so they quite expensive. It can be hundreds of euros or even thousands of euros, and most part of them is made in Europe, so now it's really difficult to obtain it. I know that in Russia there are some places when they try to make solvent extraction resin by themselves, but the main problem of this production that the resins have different properties when we're talking one sample to another sample. You buy one, it works good. You buy another sample, it works bad. So also toxic components, but I think in case of radioactive isolation of elements from irradiated targets, it's not a big problem. Also, another problem is resin degradation. This is expensive columns, and the organizations that made it, they can add a tip that you can use this resin only 10 times, for example. And after that, it becomes very expensive to use it only 10 times. And after that, the properties of resin go down. So it's expensive and it can be easily destroyed. And it has limited capacity. It's difficult to put a lot of ligand on the surface of inert part of the resin. And also there is, I think, the main difference of connection between ion exchange resins and extraction chromatography resins, because in first example, in case of ionic exchange resin, there is a chemical bond between inert surface and, for example, group of sulfuric acid. There is some kind of covalent strong bond. And in case of extraction chromatography, as you can see, we just put one lipophilic phase on another lipophilic phase. It's really low. It's really not strong bonds between these two. It's just absorption between two organic compounds, and because of it is easily to destroy this. This is a stationary phase that contains ligand. It's easy to do with acids. Is the main problem if someone puts organic substance, for example, toluene, in your extraction column, it will be destroyed at all, because toluene will destroy all this stationary organic phase. So this is all cons and some real cases. Most part of them in English, but I'm sorry for some Russian slides. First example is isolation of actinium-225. and radium-223 from thorium target that was irradiated with protons with energy about 70 megaelectron volts. First one that I want to mention here, that I think every case when we have a target with lots of produced radionuclides, we have a scheme when we use different chemical procedure. We here, of course, first procedure is a dissolution. Here, nitric acid and very small amounts, but they are really important for dissolution of thorium target. After that, as I say, in the very beginning of my lecture, we have a problem that we have large amount of target. There is no radionuclides, but its concentration really high. And first that we should do is remove this target material. And for these purposes, is really useful to make solvent extraction of this part. And in this work, this published work, the authors of this work, they have two options. They compare 3 times extraction by TBP in toluene and 2 times extraction of HDHP in toluene. And as you can see, the extraction of other elements was more interesting. So this solution was have less impurities in case of HDHP, not TBP. After that, they use 2 solvent extraction resins, is DGA resin. They obtain 3 valent elements by it, and after that they use 2 resin and obtain pure actinium-225. Another case, also here their target was irradiated. This is antimony target. It was irradiated also with a proton, and the main idea here is to obtain stannum 117M. It's used for diagnostics some kind of cancer, and it's antimony can be easily solved in H4 solution. And after that, same problem, we need to remove target material, and here easily can use such kind of easy extractant. But there is one problem when we have some macro component and micro component. Sometimes properties of micro component can be connected with the properties of macro component. And here you can see distribution ratio of stannum. And if we extract only stannum, there's a number of distribution ratios. And if we extract stannum in presence of high amount of antimony, the distribution ratios of stannum goes higher in 1 order of magnitude, for example. And here in this work, authors have made some works for understand the right conditions for isolation of target material, isolation of antimony, and yes, it's called soy extraction effect when we see increasing of distribution ratios in the presence of microcomponent. And they use 10 mol per liter chloric acid for hydrochloric acid for isolation of antimony. And also another example. Maybe you know, this is Monoblenium 29. This radionuclide is a mother radionuclide for technetium 9090M. One of the radionuclide is very wide use in the SPECT investigation and SPECT diagnostics of people. But it's really difficult to product molybdenum 99 in one of the best ways that have very high yields of production is irradiation of the uranium dioxide with very high amount of uranium-235 in it. Unfortunately, now this wave production is banned. It's impossible to give your molybdenum 99 to the international organization if you say that use this method. And also in this case, they're quite difficult task, more difficult than in the last two examples, because if you use such kind of uranium as a target material, it's really expensive. It's impossible expensive material for target. And you need to obtain molybdenum, and you also need to reuse your uranium. So this is task called as isolation of both uranium and molybdenum. For example, here we don't know the fate of thorium after this separation. We can remove it, we can put it in the waste and so on. But here it's very important to take uranium back and make new new target from it. And here we use combination of two extractants. Sometimes when we use two extractants, we can obtain so-called synergetic effect. You can see here, for example, distribution ratios. Here is a distribution ratio of TBP, pure TBP. And here you can see distribution ratio, some kind of HDHP extractant. And if we mix them up with the same concentration, you can see how distribution of ratios goes higher. So it's an example of synergetic effect. And also this synergetic effect have effect on scrubbing of molybdenum from organic phase. And because of these properties of such kind of system, we can obtain two pure products: uranium that we use for production new target, and molybdenum that we use for production of technetium 99M. And another problem, for example, is Cerium 144. This is radionuclides that use in fundamental studies of neutrino. And very often French colleagues buy this radionuclide from the Mayak facility. It's wonderful thing that even Cerium has some kind of redox chemistry that make possible to remove it from HLV, high-level waste. High-level waste in general is really difficult solution. There's elements from antimony to curium, so about half of periodical table. And another problem that besides cerium, there are other lanthanides, and in case of lanthanides, we have very similar chemical properties. The stable oxidation state is a +3 in aqueous solution. But we can oxidize cerium to oxidation state +4, and in this case, it can be easily removed because in this condition, its chemical and extraction properties is really different from other lanthanides. And when there was made some experiments in test tube, it was easily oxidized by such kind of oxidizer. And after this oxidation, the distribution ratios go higher in even 2 orders of magnitude. So we can easily separate cerium. But when it was used, a real example of HLV, they add one equivalent of oxidizer. There was no extraction. Of course, the investigators, first the idea was there is no oxidizing of cerium, and they give more and more equivalents of oxidizer, and they saw that oxidation can occur in case of 10 equivalents of oxidizing agent, and only in these conditions they obtain cerium extraction like it was in the test tube. And so, a great question, why it happened? The idea is easy because cerium +4 easily reduced by the product of radiolysis. The actual high-level waste they called high-level because there's a huge, giant amount of radioactivity and lots of radiolysis products or radiolysis of water products. Most part of that can act as a reducing agent, and these reducing agents, they reduce Cerium from +4 to 3,4 state. Another problem, for example, another case is the production of terbium from europium, stable europium. Once more time, lanthanides have really close chemical properties, and when we have task to separate one from other, it's really difficult. There are only two special cases. One was Cerium +4, second one is europium. But in contrary with Cerium, we can reduce europium to europium +2. And if you use such kind of nuclear reaction, when we irradiate europium by alpha particles, we obtained not the closest lanthanide, but lanthanide after one terbium. And because of it, the separation will be quite easy. Sometimes, for example, some investigator use oxygen ions to, for example, if we will irradiate europium with them, we can obtain, for example, erbium, and separation will be more easier than to neighbor lanthanide. The separation between europium and erbium is easier in this way. And so there's also a problem that after we reduct europium to oxidation state +2, we should stabilize it, and the easiest way to stabilize it is to use precipitation. But there's also some problem. There's some also investigation on the proper conditions for this, and also we need to use some kind of high amount of reduction agent. As reduction agent, there here was used acetate acid, sulfuric acid, and hydrochloric acid, and they saw that the sulfuric acid is most common here because sulfate of europium +2 can form precipitate in this condition. And after that, as I say, precipitation is not very selective technique. We obtained some small amounts of europium in this terbium, and they was used solvent extraction chromatography, and here was used LN resin or special resin for lanthanides. And here you also can see that the base separation was obtained in case of dilute nitric acid, because in case of higher amounts of acid, the chemical behavior of lanthanides becomes very close, and only in different nitric acid we have find some difference in it. Also, we can see that not only terbium was produced, also gadolinium, and it goes with europium. And one more time, this is a full scheme that I showed to you in the beginning. As I say, that was used for isolation of actinium and for isolation of radium, and there was used some hint. We say that strontium resin, just by name, we can understand that it's properly used for isolation of strontium. But sometimes, if you want to isolate metals that have charge 2+ from metals that have another charges, you can use this resin for example, radium. And here, in two parts of the scheme, there's also one feature that after extraction of organic phase by HDHP in toluene, in this organic phase, there was accumulation of radium-223 from actinium 227. And if we wait for some time, we can also have some, we can also make some isolation of radium and use this kind of resin. So there's also some chromatography problems of use of lanthanide resin for actinium-225. When we use also quite higher, quite high concentration acid, there is no separation. In this case, they use a more dilute acid. for isolation. And very brief summary. There are some different chemical ways of isolation. First one is precipitation, eye exchange, extraction chromatography, and solvent extraction. Extraction chromatography is a combination of two techniques, and because of it, it is a state art with very high selectivity, and we can make even individual nucleus columns for each one of nuclides that we want to isolate. Very often, precipitation solvent extraction is used for removing target material from bulk matrix, from target material, and it will be shown in more detail in lecture from Mr. Leib about practical issues when we want to try it in our lab. So thank you for your attention. Any question? Yes.
Thank you very much for time. I just wanted to know about the dry distillation method. For example, distillation of iodide.
Okay.
Target tellurium dioxide. Is dry distillation?
Well, I think I can answer to you later. Okay. No more question. Okay. Thank you very much again.
Guys, let's go to have a lunch with Yulia together.
Yes, yeah.
Иванович, добрый день.
Здравствуйте, здравствуйте.
Вас видно. У вас там есть кнопочка демонстрации экрана? Все нормально?
Да-да-да, сейчас я найду ее. Я найду ее. Что-то я не вижу ее пока что.
Тогда секунду.
Есть, нашел.
Ага.
Один момент. Знаете, написано, что disabled. Это Владимир, да?
Да. Ага.
Хорошо.
сейчас попробуйте.
Ага. Так, все появилось. Сейчас я запущу.
Угу.
Все появилось, да?
Да, все.
Ну, отлично, отлично. Ждем, значит, тогда несколько минут.
Да, ага. Ну что, я думаю, можно будет уже начинать. So, dear colleagues, dear participants, now we will have a lecture from Michael Ojovan, professor, also from our university, but not only. I think Professor Ojovan will present himself better. And what I would like to say that he is expert for a very long time in radioactive waste management, and today you see the topic. It will be this lecture will be related to nuclear and also radiopharmaceutical waste management that is important for, of course, medical applications, etc. So, Professor Ojovan, please, the floor is yours.
Thank you, Professor Petrov. So, good afternoon, dear colleagues. I'm Michael Ojovan. This International Winter School on Radiochemistry is focused on radiopharmaceuticals. And because of that, it's here this lecture, which is about radioactive waste management or nuclear waste management, but with half of it or a big part of it, it's on radiopharmaceutical waste. So the first part of it will be there. So you see here on this slide my affiliation. My immediate past, it's not so immediate. So it's a couple of years ago, I left the International Atomic Energy Agency, where I worked for almost 8 years in a Department of Nuclear Energy of IAEA, International Atomic Energy Agency, which is in Vienna, where I dealt with the mainly pre-disposal management of radioactive waste. And after that, I returned to academic work. So indeed, I'm affiliated with the Moscow State University, Lomonosov Moscow State University, Radiochemistry Department. Also, I work for the University of Sheffield, which is in the United Kingdom. I worked there from 2002, so a very long time. And from 2011, I'm affiliated with the Imperial College London, which is naturally it's in London. Yes, but also I keep now, you see here, this label here on my slide. This is the journal published by the Hindavi jointly with Wiley, which is Science and Technology of Nuclear Installation. So I'm a chief editor of this journal. So you're welcome to publish. It's an open access journal. So the content of my lecture, it is here. You see that I will introduce you. A big part of it is on radiopharmaceutical waste. So I will go through explaining how this waste appears, what is a part of radioactive waste. And because of that, the large part of my lecture, which is in black color here, you see it's about actually radioactive waste management activities. So all the stuff which belongs to that, I will try to very briefly, of course, this is so-called helicopter view, explain to you with some references, so you will be able to have a glance view on all that and understanding of key issues, key approach on radioactive waste management, and of course that after that you can enter into details and in many parts of it. So let's start with the brief introduction. So we are speaking about the waste, radioactive waste or nuclear waste. And in this slide, you see in the upper part of it, if it is waste, that's a material that nobody needs it. So throw it away, we don't need it. And this can be gaseous waste. So we are driving our cars and from the back of it, we are releasing into atmosphere the production of combustion in the engine. So we don't need these gases, and it's too expensive to collect them and to dispose them. So they are not dangerous, let's say, for environment. They can be liquid, so we are washing the dishes in our kitchen, and this wastewater is then discharged. And solid, of course, we generate a lot of so-called municipal waste that arises from just day-by-day life. So we throw this away, so solid waste. When we speak about radioactive waste, so this is the definition. It is given here in a red color, you see here. And it's synonym, radioactive or nuclear waste, because the radioactivity, it comes from nucleus. So this is the waste. You see the definition that contains or is contaminated with radionuclides at concentrations equal or greater than clearance levels established by the regulatory body. So what is the point? The point is that in reality, everything around us, including our bodies, are radioactive. Perhaps you know that already, all of you. I see some faces that that a little bit I recognize, so maybe you attended some previous courses where I was also teaching lectures. So I'm not telling this the first time, and many of other professors are telling you. You sometimes can read from books and so on, that we contain a lot of tritium, we contain a lot of carbon-14, which is a long-lived radionuclide, and the content of carbon-14 in our body, which is decaying, is constant. And only after we are not anymore alive, the content started to decrease, and then we have this dating. So it is possible to establish exactly when a human died by the content of carbon-14 in its body. So the point is that in any country, in all countries, the authorities of the country establish some level of activity. And this level, if the material, which is waste, nobody needs it, the content is higher than these clearance levels, then this waste is radioactive waste. And everybody is very worried about it, and they are trying to take care of it, and so on and so on. It depends, of course, on content. If we are speaking about high-level waste and fuel and so on, these are huge levels, much higher than the clearance levels. But if you look about things that are very close to it, then the danger is not real very high. It's something that we have to live with, and most probably that without this small radioactivity, the life would not be possible at all. Okay, so the definition of radioactive waste is pure for legal and regulatory purposes. So we need always to rely on clearance levels. And it's not in my slides, but these levels are recommended by the IAEA, International Atomic Energy Agency. And most of the countries take the IAEA levels and use them. Some of them modify them. It depends on the situation, which are extremely conservative, by the way. So it means they are very low. Okay, so if you look on radioactive waste origins and types, here it's a picture. So you see the globe in red color, the countries that operate nuclear power plants. So they use nuclear energy on a large scale. They produce electricity, energy using nuclear power plants. And naturally that they produce a radioactive waste. Compared with other industries, these are minuscule amounts of the waste. Then in this bluish country, the color, the country that use research reactors, so they also produce some radioactive waste. And then this is DSRS, means disused sealed radioactive sources, and practically they are everywhere, even under these colors that are red here and bluish here. The disused sealed radioactive sources are produced. And then some pictures. So front end fuel facility, that means facility that produce nuclear fuel. Then there are some so-called RTGs, so thermoelectrical generators that use radioisotope decaying to generate electricity. So a number of pictures here that just to illustrate the appearance of nuclear waste. In order to have a language to speak about the radioactive waste, it was internationally agreed to have classification of radioactive waste. Although in countries, particularly in the countries that started to use nuclear energy from the very beginning, like United States, former Soviet Union, United Kingdom, France, other countries, of course, they still use their historically established classification of radioactive waste, but it was agreed through IAEA on this internationally accepted classification of radioactive waste, which start with the so-called exempt waste. That means the waste which can have radioactivity, of course, natural one. But because the levels are below clearance levels, it is called exempt. So this is, we can say, non-radioactive waste, but we understand that there is some radioactivity there. It's just exempt. So from the very beginning, regulatory authority doesn't care on it. So this is not our business because there is really no any hazard from it. Okay, then you see here very short-lived waste. It means the waste that very quickly decay. So if in 10 days or 1 month, due to the decay, they disappear naturally. These are called short-lived waste. Then we got very low-level waste. So they are above the clearance level, but not very high from there. So maybe 10 times, maybe even 100 times, but not 1,000, 10,000. So these are very low-level waste. So the hazard from this waste is low, is even very low. So because of that, the name. Then we got low-level waste. So they need care, they need processing, they need careful disposal, careful storage, and so on. So there is a real hazard from the waste. Then intermediate level waste, and sorry, it is covered here by the picture, but this is high level waste, And the agency and the classification schemes everywhere, they speak in terms of two parameters. The first one is the radioactivity. The higher is radioactivity, we are moving here to high level waste. And half-lives. If we have the half-life more than 30 years, we say long-lived waste. If less, we say short-lived waste. But if the lifetime is several months and shorter, can be seconds, then we speak about very short-lived waste. So we now understand the language and we can look to this inventories. So here it is like the global inventory published by the IAEA. So it is not very recent, but nevertheless, we can have the impression about the cubic meters accumulated globally. So once again, if you look to these cubic meters, the total cubic meters compared with the other industries, they are we cannot see them in the slide if you try to put them in a normal scale. We have to use logarithmic scale, and even then they will see very small bars on the plot. Here in this slide, we can look to the typical sources of low-level waste. So we have nuclear fuel cycle facilities, nuclear power plants, they generate low-level waste. Then we have research and development and medical facilities. We see that's the topic of this year's school. Radiopharmaceuticals are a part of research and development and of use in medicine. So it's here, decommissioning of laboratories, of facilities, and so on. Environmental remediation activities, so they generate low-level waste. Intermediate level waste, again, nuclear power plants generate some intermediate level waste, then reprocessing of nuclear fuel to produce new fuel, decommissioning, and you see here, these used sealed radioactive sources, they are not low-level waste. They belong typically belong to intermediate level waste. Then we got here in this slide some examples. So trash from process and laboratories, which is higher than clearance levels, and because of that is radioactive waste. Then protective equipment, oils, pipes, ion exchange resins, soils, decontamination solutions, pond liquids, etc. Then examples of intermediate level waste. And here we can see again ion exchange resins, which are typically used in purification, cleaning of the water, and so on. Some sludge and flocks, and other that appear from an iodine, let's say, that can appear also from medical uses. And high-level waste, which is from reprocessing of fuel, so it's out of interest of this school. Everywhere practically is the same picture like shown here. So if you look to the waste volume of the radioactive waste, then typically you see here globally 96% by the volume is low-level waste. Then we have about 2%, this is intermediate level waste by volume, 1% very low level, and 1% high level waste. That's by volume. Spent nuclear fuel, for your information, it is always considered separately, because in some countries it's decided that they use so-called open nuclear fuel cycle. So the fuel which is once used in the reactor and very small part of it is really producing electricity. It can be reprocessed and used again and again and again. So it's a lot of useful material there. But in some countries, let's say Sweden, Finland, yes, United States currently, they, after usage of the fuel, this is declared as waste and is disposed of. In some countries like Russian Federation, where you are sitting now, United Kingdom, France, they reprocess the fuel and produce new fuel in order to be used in reactors. So now we move to our chunk, to our part, medical part, research part, which is on radiopharmaceutical, including, yes, so non-nuclear fuel cycle. So they are also termed institutional waste or institutional radioactive waste or institutional nuclear waste, institutional. So that's because of application of radioactive materials, radiation in medicine, industry, agriculture, in research. Let's say research reactors operate in mining, in chemical, and some pictures here. So in the past, lighting conductors were used, which could contain, let's say, radium-226, in order to avoid striking of lightnings to buildings and to cause big troubles. These are radioisotope thermoelectrical generators. The height is approximately the height of a human. So these are big devices. And inside, typically, we can have plutonium or most typically strontium-90. Huge activities. This the question of thousands and thousands of Curie. So it's generating heat, which is transformed into electricity, and they can be left in Arctic regions and mountains where nobody can come there, and let's say can serve to generate to guide the planes which are flying and so on. And here, medicine, teletherapy machine that say gamma knife, which can kill the tumors in patients, and by this treatment to save the lives and to prolong the lives of the people. So radiopharmaceutical waste, once again, non-nuclear fuel cycle waste is generated by hospitals, universities, mainly in Western countries, research laboratories, oil and gas industry, some non-nuclear industries. Let's say this picture, if you look in many rooms, these are smoke detectors. There is typically a small amount of americium or plutonium there, and it signals, trigger a signal that there is smoke inside, there is a fire, so that serves to. So they are continuously operating, no need to put a battery inside, and so on and so on. So again, some devices of industry, and here it's again a use in medicine for the treatment. I put here this information just to show to you for a country like United Kingdom about it. There are many small users which use nuclear energy in form of shield sources or sources of radiation, and the numbers it's about 1,000, and they don't have. If you speak about nuclear power plants, then these are huge facilities with dedicated personnel, well educated to care, to deal with radioactivities, with radioactive materials and so on. If you speak about small users, then of course that regulator should strongly supervise all kind of operations in such facilities because they lack personnel, even medical institutions, let's say hospitals and so on and so on. So because of the risk associated with the presence of radionuclides in applications of nuclear energy, so radioactive materials in non-nuclear fuel cycle institutions, the waste which is generated during the production and use of radiopharmaceuticals, it cannot be discarded, so to throw just away in the same way as normal waste. And specific rules and procedures have to be followed. So these procedures may vary slightly depending on national legislation. But some basic principles have to be followed everywhere. And here the IAEA, at International Atomic Energy Agency, plays a very important role because it publishes guidance documents, standards, and technical documents which can be used as guidances everywhere as examples. Of course, the processing of radioactive waste is expensive, and the cost can be high. And that may vary significantly depending on physical state of the waste. And we should take all measures to avoid the generation of unneeded radioactive waste. These slides give a site of IAEA, which is dedicated to radioactive waste management related to medicine. So you see here, it is called Human Health Campus. It's just copy paste from the site. The link is operational here. So if you'll click on this link, I'll send via organizers the lecture. So you can find by search, of course, through Google now you can find easily everything. So this is a link to the site when you can find more information, guidances about how to manage, how to deal, how to collect the radioactive waste which appears in medical institutions. So the first guidance is that all radioactive waste must be carefully sorted into different categories. Each of these have certain processing requirements. So we see here that different bags with different colors. So big institutions, they have special instructive materials. So they collect the radioactive waste which is produced after application of radionuclides in separate bins and separate rooms and so on and so on. So what are the typical radioactive waste on the use of radiopharmaceuticals, production and use? So when we produce the radioactive materials and use it, radioactive waste is generated in different forms. And generically, this waste comprises the radioactive materials that is no longer useful. And because of that, nobody needs it, and this is the waste. Even can be your source of radiation, sealed radioactive source, but if nobody needs it, it becomes disused sealed radioactive source. It's waste. Items that have became contaminated because they were in contact with radioactivity can be some paper, can be some plastic gloves, covers, and so on. Can be measuring devices, so counting tubes, glassware, washing liquids, excreta from patients or from some animals and so on that they were administered the radiopharmaceuticals. We need to collect this excreta, and that material, if the levels is higher than clearance level, is radioactive waste. When we produce then the radiopharmaceuticals, we use typically particle accelerators or research or nuclear reactors, typically research reactors. Not nuclear power plants are not involved in these activities. So they are used to produce radionuclides, which are then joined with special chemicals, so they become radiopharmaceuticals. And the radionuclides generated in particle accelerators and reactors are typically producing, we say, the targets. We take these targets, they work by a beam of accelerator. So we say this is a target, or it's a capsule that they put in the reactor, and the material is there inside. And then we remove this capsule, this target, to process. And then the months after processing, it's waste. Then we during the processing of these targets, this capsule, we have some small, of course, but some volumes of liquid waste, The activities can be even high after this irradiation, can be some volumes of dry, low-level solid waste generated. So this is radioactive waste. If we speak about the usage of radioactivity in radiopharmaceuticals, then we have two different forms. The first one, it is sealed radioactive sources. So this is when we use in a form of which the probability of dispersion of radioactive contents is very low. So we have a material which is sealed inside of durable capsule because of that, say, sealed radioactive source. So the radiation is coming out through the walls of this capsule, but the material is kept safely inside. It's hermetically there. And the producer warranty that during a certain time, if operated in the conditions that again are prescribed by the producer, it's warranted that the material is kept inside safely. So it's sealed radioactive source, or can be open source. We say unsealed source. So the material is dispersible. Also, it is combined with the chemical medium in which they are apart. So it's not the question that the pure radionuclide is going to be. It can be, by the way. So I'm sorry, because let's say if we speak about iodine, it can be that it's just a gas. Okay. If we speak about carbon, let's say 14 or other carbon 11 and so on, it can be CO2 to be breathed by the patient, let's say. But we can inject even the pure. So yes, can be combined with a chemical medium, typically just to administrate it to a necessary organ in the body. Because of that, we use special chemicals that are preferable if they move to a certain part of the body. So the biologists know how to find these pharmaceuticals, which combined with the radioactive element, they become radiopharmaceutical. So then a number of tables, colleagues, I will show to you. They are taken from a specific safety guide of the agency, recently published by the IAEA, where we can see the information of main unsealed radioactive sources, and then will be table about sealed radioactive sources. So there are many such tables, so I will not go into details to all of them, so don't worry, not will bore you. But what is in this table? The first column is the actually radionuclide. So we start with the hydrogen, so this tritium. So it is unstable. It decays with the half-life 12.3 annums, so years, and is typically used in radio labeling. So we use it, that will signal that is there. Biological research, organic synthesis. The activity typically it's up to 50 gigabecquerel. Typically, so can be different, but typically no more than 50 gigabecquerel. And the waste characteristic is that they typically are in solvents, they are in solid or liquid form. And then we can move to others. So carbon can be 11, which is just 20 minutes, 20.4 minutes, and decays half-life, it is a half of it gone. It is in positron emission tomography in lung ventilation studies. So that's where this CO2 we administrate to the patient. Activity up to 2 gigabecquerel solid and liquid, and then we move to other. So the table here gives you a detailed information which is collected throughout the world, published by the IAEA about many typical radionuclides: sodium, phosphorus, oxygen, fluorine in positron again emission tomography, very important, 1.8 hours the half-life. And we move sulfur, chlorine, chromium, then and so on, cobalt, here difficult to read. So we move to heavier and heavier radionuclides. So we see the gold 198, 2.7 days. It is for therapeutic nuclear medicine and also for diagnosis, of course. Up to 500 megabecquerel, the waste is solid or liquid. Then thulium, mercury. So the radioactive waste generated can be liquid, solid, or gaseous. Then the liquid waste may be further subdivided. So we can say aqueous waste, so the basis is water, and organic waste, so some organic material, oil, something like that. Solid waste can be also subdivided. We can say that it's compressible waste, non-compressible waste, maybe it's a metal or it's a piece of concrete, so how to compress it. Combustibles on paper that can be burned. Non-combustible, again, some inorganic materials like some metallic pieces and so on, they are non-combustible waste. So briefly, aqueous radioactive waste. So based on water solutions, but can be some suspended particles. Because of that, we say aqueous radioactive waste, not just solutions. So it's not, can be some colloids there, can be some sludges there, so it's aqueous. So at the radioisotope production facilities, it results this aqueous radioactive waste from chemical processing. So we from the target extract the necessary radionuclides. We use chemicals, basically solutions based on water. So we can make etching, dissolving target materials. Solutions is of small volume. It's normally contaminated with radionuclide impurities because not all radionuclides generated by bombarding the target is necessary to us. We extract, let's say, this actinium-225, and the other actinium to us is not good, and other that also are there. And depending on chemical process used, the aqueous waste may be chemically very reactive. So can be the pH very, very low or very, very high, so they can be reactive. In the hospitals, it depends on technique used in therapeutic and diagnostic nuclear medicine. Typically, most of the radionuclides used for diagnosis are very short-lived, so very short-lived, so the half-life is less than 10 days, very typical. It means that if you will keep safely somewhere this waste, for 10 days, a half of radioactivity is gone. So if it is still above the clearance level, other 10 days, another half is gone. So that's guidance to us that delay for decay, it's an approach to deal with this waste. Okay, then we have research where we study metabolic pathways to develop, let's say, new medical drugs and so on. We use animals, mouses, and so on. So they may be involved in various investigations, and we then inject into them some radionuclides, and then the bodies, the blood, excreta, carcasses, bedding of these materials that they were leaving until we do this research. This can be radioactive waste. And also, this can be a part of liquid radioactive waste, some urine from them, some washing that we are cleaning there, and so on. In some cases can be longer lived radionuclides, so not necessarily very short lived. So because of that, and some microsphere can be used to put into the bodies and so on. And in some organizations, the bodies are maceration. It is used. This is when we crush this body we make them like a very viscous liquid. So it's everything. It is crushed in a form of flowing material, the body. So that's like a liquid. So it goes together with aqueous radioactive waste because most part of the bodies of animals and of us is just water. Also from neutron activation analysis, we can generate radioactive waste. In research centers, liquid waste may be contaminated with both short-lived radionuclides, but can be even carbon-14, which is a long-lived radionuclide. So that's typically long-lived radionuclides. They must be disposed of in geological repository if activity, of course, is enough high. The volumes of liquid radioactive waste is typically not high. The waste from radio labeling may have relative high activity concentrations and should generally be kept separate from lower activity wash solutions. And it's unlikely that alpha-emitting radionuclides, other than uranium and thorium compounds, or relatively longer-lived radionuclides containing cesium and cobalt, will be used. Irrespective of the field of the work, contaminated equipment and facilities are typically, so may need to be cleaned. We say decontaminated or disinfected. This is done in order to avoid any biological contamination, and that results in radioactive aqueous waste. And then again, we can have radioactive and a biological hazard. So the point is also that this waste during the washing, cleaning, disinfection, they can contain also complexing agents that may cause later problems in processing of this waste. Short slide about liquid organic radioactive waste. So typically this is due to the vacuum pump oil, lubricating oil, hydraulic fluids, scintillation solutions from analytical laboratories, solvents from research, or solvent extraction uranium refining, like the previous lecture given by the Piotr Matveyev, so about TBP and other solvent extraction methods, so materials that are used there. If you completed the work, then this material becomes radioactive waste, and if the contamination is above clearance levels, it's really radioactive waste, not exempt waste. The volume of liquid organic waste produced from nuclear applications is generally small, even compared with other categories of radioactive waste generated. Scintillations liquids normally result from measurement. So that was in the lecture of Piotr Matveyev. They can contain these beta and gamma emitters that were identified during the measurements. So during the separation procedures that he described to you. And the most common are carbon 14, can be iodine 125, sulfur 35, less common, but can be anything that we work with. Typically their volume is not high. Then solid radioactive waste. So most of solid waste generated in medical and research laboratories, they falls into the category of combustible, most of this waste. So that's paper towels, swabs, papers, cardboard, plastics, rubber gloves that are used, so protective equipment, protective clothing, masks. Can be animal carcasses from research, biological material, can be a smaller amount of non-combustible waste. So some vessels, some glassware, some scrap metal, waste from decommissioning or facilities in which radionuclides were used. So that's again about the typical materials that represent the solid radioactive waste. So frequently, such material is only slightly contaminated, and possible it is no really above the clearance levels. So I can tell you from the history of nuclear power plants. So everything which is generated in nuclear power plants in the control zone, it is declared radioactive waste. Just is labeled as radioactive waste. So it's said by definition, this is radioactive waste. The same it is done in many laboratories that deal with radioactive nuclides. And then they are checked. And if this waste is non-contaminated at all, or the contamination is much below, it's below, let's say, formally below the clearance level, then it is clear. So it was identified, so we need to do measurements. And so it was declared radioactive waste, but in reality is non-radioactive waste. And because of that can be cleared from regulatory control under the strict control with the approval from regulatory organizations and so on. Notice again to declare this is non-radioactive waste. That is not possible. So then they will go with industrial waste, with municipal waste and so on, because it's formally non-radioactive, although just the levels are below clearance levels, some natural radioactivity is still there, so it does not disappear. But some of the items, of course, can be significantly contaminated. So that approach which is used in nuclear power plants and in serious laboratories with work with significant amount of radioactivity, that approach, it is universally used everywhere. Okay, so here it's about the radioactive contaminated material and equipment may be generated in medical activities and research activities and may consist of components of dismantled equipment, rigs, surgical implants. That material can be glass, can be plastic, and the activity, of course, differs. Can be just some materials which is activated, so can be some shielding material. But if the radiation was, let's say, some neutron irradiation, then the material will be activated and the radionuclides will appear in the material. Although at the beginning this material was clean of radioactivity, nothing radioactive was there, but the activation materials were created. So maybe due to the neutron activation, some cobalt-60 was formed. So let me just tell you, the graphite, which is used as moderator in reactors, at the beginning of the use, it's absolutely not radioactive. It's a very, very clean material, the cleanest material on the earth, let's say. It's very almost pure carbon. So it's carbon 12, can be little, it's very, very small amount of carbon 13 and no carbon 14. But during operation, due to the processes that occur in reactors, it became, and particularly because of a little, very small amounts of contamination by iron during the cutting of these blocks of graphite. Then we can find cobalt 60 in the graphite generated by nuclear reactors. Okay, so animal carcasses, they can have activity concentrations depend on species of the animal and experiment procedures. Carcasses may present biological and chemical hazards, so that should be carefully considered. And because of that, typically the carcasses are kept in refrigerators to avoid, you know, any putrefaction and things like that. Also can be contaminated with long-lived radionuclides, so that particular attention should be to them. And finally, gaseous radioactive waste can be also appear due to the application of radiopharmaceuticals. So can be used gases like xenon, like krypton, technetium-99, which appears after the decay of molybdenum. It was emphasized to you in the lecture of previous lecture. In positron emitters, it's fluorine 18 and carbon 11 in investigation of ventilation of the lung. And very important are disused sealed radioactive sources. So they are initially sealed radioactive sources. They are used widely, practically everywhere in all the countries. So the activity of sources, it's typically extremely high. So if in a gamma knife, let's say that the activity are so high that within some minutes the dose that a human can obtain if full body is irradiated by this source, it's lethal. So no way to escape from the death. But it's shielded, so only a thin beam it is allowed to come out of this device, gamma knife, for therapeutic, focus it on the tumor and is killing only the tumor. But after a certain period of operation, some 10 years or so on, the activity is not enough. So the processing time becomes too long, and the source should be replaced by new one. And this becomes a disused sealed radioactive source. Nobody needs it. The activity is not so high to be used there in the device. But nevertheless, the activity is so high that the danger from this material is extremely high, and the dose still can be lethal from this source, which is like a finger. It is like a pencil. It's a small piece, and can be so dangerous that it's like spent nuclear fuel, which is in a reactor, or the dose rates can be even higher than from a bundle of spent nuclear fuel. Here are the tables. So you can see here again the radionuclides typically used in manual brachytherapy. So this is a medical therapeutic procedures where the radiation it is used again to kill the tumors. And you see a range of radionuclides. The approach is the same: radionuclide, the half-life, the source activity, which is typical, and can be quite high radioactivities. And if you look to the cesium, you see here in remote afterloading brachytherapy, so it is kept the source in a shielding material, but during the application to the patient, it is taken out from the shielding and is put, let's say, very close to the tumor. So that is called afterloading brachytherapy. Maybe you got this information from other lectures, so sorry. Can be whole blood irradiation, sterilization. Extremely high radiation fields are used to kill all kinds of the species. So can be, you see here, 40 petabecquerel. So these are fixed installations. So the material to be irradiated for sterilization, it is brought inside of the machine. There is irradiated and then is sterile. So there is no anything there that survive such high doses. Can be small sources, the so-called calibration sources that are used to calibrate the dosimeters and so on. Then the activities are really very small, and the danger from these sources is not high. Although all of these are also disused sealed, can be disused sealed radioactive sources. You can see here the continuation of these tables. So again, all of the activity of external beam and other large source may be fallen below useful levels. The potential for injury from such sources remains substantial. And in particular, external beam radiotherapy sources normally contain cesium 137, and it is in dispersible form. Moreover, very often it is cesium fluoride, so it is even soluble form inside of this cell source, and present a severe hazard if their primary containment is breached. So that's a summary of radiopharmaceutical waste that as a result of initial production of radioactive material and subsequent use, radioactive waste in various forms is generated. Waste of variable composition may also arise from incidents involving radioactive materials, the risk associated with radioactive waste, and thus precautions that should be taken vary widely depending on the application of radionuclides and quantities. And now I move to the second part. There is no here break because I have very limited time, another half of hour or something like that, 35 minutes. So let's look on generic radioactive waste management activities. So here in the slide, I'm starting to the very important statements that radioactive waste management is a national responsibility. Although we have such important international organizations, this representative of most of, so we say, member states, currently 175 countries in the world are member states of IAEA. And most of these countries have some staff members. So I worked for almost 8 years in the agency as a representative of United Kingdom. So I was there as a staff member during this time. So I was international servant, not belonging to anymore to United Kingdom, but then I returned back. So all the countries. So you are here from Belarus, of course. Many Belarusian experts are in the IAEA working from Egypt. Many people from Egypt, experts that I knew personally, are working there, and so on. So sorry, not Russian Federation, Iraq, and so on. People that are here in the list. So sorry, not noting all of you. And it's very important that we care about radioactive waste because that provides us the means of viability and public acceptance of nuclear energy, not just to produce electricity in nuclear power plants, but also in medicine and so on. So we need to manage properly radioactive waste and to show to everyone, to all the public, that we do that properly. We care about radioactive waste, and this is done safely. And safety is ensured both for today and for tomorrow, for the future generations. So that's important. The end point of radioactive waste management is always disposal. So it's final when we put the waste, and let's say forget about it. We are not forgetting, of course. We know where is the site. We monitor for a long period of time this site, and so on and so on. But it means we are not anymore doing anything to ensure the safety. We dispose of, and the disposal is safely keeping the radioactivities there. And key to achieve this is the development of integrated waste strategies, so to account for everything during the whole life cycle of radioactive waste. So when we manage radioactive waste, we have got two types of activity. The first type, it is administrative activities, and then the processes that we do. So if you speak about administrative activities, we are dealing with the so-called management systems. There are guidance documents in the agency about that. So we have waste management planning. We establish the inventory and then characterization. The previous lecture, characterization, measurements, it's very important. Otherwise, how to know, is this low level waste, intermediate, what kind of the waste? We need to measure, to do characterization. Then we develop for waste acceptance criteria for a storage facility, for a processing facility, for a disposal facility. We select technology process. So this is administrative activity. We estimate, of course, costs and try to optimize that, not put all the resources into this, so to optimize that. Then we obtain the licensing. We provide safety case that shows that everything that we do is safe. And then we go to the main waste management operations. So we go to operational activities. And this is a picture taken again from IAEA. So we say radioactive waste management, we have pre-disposal and disposal. But if you take a radioactive material, it doesn't mean that a part of it goes to pre-disposal and a part to disposal. No, everything goes to pre-disposal, where we have processing, we have storage, we have transport, and in the processing, we have pre-treatment, we have treatment, we have conditioning. And when we do this, only after that, we go to the disposal. So it's a lot of stuff to be done before the waste will be accepted to the disposal. a large field of activities, So here there are some pictures of IEA documents and not only of publications that are relevant, let's say, references. Okay. So if we work with say, nuclear materials that are radioactive because of the decay of radionuclides there. So in this part are useful materials, leave them. This part, we speak about waste. So no further use. So the materials that nobody needs. What are the options? The first option is clearance. So if we measure, we do characterization, identify that it's below the clearance level, we clear it from regulatory control of nuclear authorities, radiation control, nuclear authorities, and this is normal material, we say, non-radioactive materials. There is some activity there because everything is radioactive. So that is treated as normal refuse, it's still waste. So no more under regulatory control of nuclear authorities. Authorized discharge, it is when we speak about some gaseous effluents, some waters contaminated. They go not under the clearance, then under the discharge. In the very old times that nobody in this room knows because you are too young to know that, they were let's say together. But currently, everywhere and agencies providing this guidance, solid materials go under the clearance if they are non-hazardous. Liquid and gaseous materials under the discharge, again, if there is no any hazard to expect it from them. And if we cannot do that, then we have to work and to prepare the material for a regulated disposal. So this is routing. This is, we need a kind of roadmap. So this is the generic roadmap of the life cycle of the radioactive or nuclear waste. So the waste is generated, then it goes through pretreatment, treatment, conditioning, interim storage, transportation to where? To the disposal. And disposal can be deep underground disposal. This is for long-lived waste and highly radioactive materials. Near surface disposal, this is for low-level waste. Or if you are lucky, we can go with the very low-level waste, very short-lived waste to the landfill. To the landfill because the hazard it's not so high, so we can dispose this waste together with municipal waste or industrial waste and like this. The definitions are in this slide, but we have them later in the next slides. So we look now very briefly to the so-called management roadmaps. If you have this waste, which is collected somehow, then following some roadmaps in the centers where the waste is dealt with, they are separated in different streams, like schematically shown here. This is actually a roadmap taken from an organization which is not far from you where you are now sitting. So this is not the city of Moscow. It is near the city of so-called, near the city. So this is city of Sergiev Posad, about maybe 80 kilometers from Moscow. And the organization has the name Radon. So it's Scientific and Industrial Association, Radon, federal organization, which have a lot of units, facilities that deal with different streams of radioactive waste. So the waste is separated in sealed radioactive sources, low intermediate level waste, then liquid and solid, then combustible and non-combustible, large size solid, soils, resins, biological waste. Then they go to different processing activities, and then they go to long-term storage, and they are awaiting disposal. The guidance on how to operate these roadmaps, how to deal with radioactive waste are in this IEA document and in this book that this is already the third edition. It was first published in 2005. You can see, by the way, here so this is my name. This is Professor Lee from Imperial College, London. This is actually the Dean of Chemical Department and head of the Radiochemical Department of Radiochemistry of Moscow State University, Professor Kalmykov. So we published this book, but it's used since 2005 as a basic manual in UK universities, still not used in Russia. There is no Russian version of it, but there is British version, already third edition, and the Chinese are translating this book into Chinese. So if you look to the IEA guidance, then there is a very good publication, Policy and Strategies for Radioactive Waste Management, with the good summary tables about inventory strategy and planning, what to do, about discharge and decay, what to do, just summaries, to have a generic information about how to deal with low intermediate level waste, how to deal with high level waste, how their disposal in different countries is organized. And these tables, I'm not going into details because I am limited by the time, but that is in these policy and strategies for radioactive waste management that I'm advising, particularly the people who are going to work in regulatory organizations. You'll have on the table a very good guidance for many things that in your life you will need. So the roadmaps, if you summarize them for liquid waste, you see we are starting with characterization and segregation, and then you see we follow the IAEA classification. So we start with exempt waste, and then we go to the discharge to environment. A very short-lived waste, very low-level waste, low-level, intermediate, high-level waste. If we speak about solid waste, then exempt waste, so it doesn't go at all into the radioactive stuff. So we go to the disposal and non-radioactive waste. Very short-lived waste, we just wait due to the decay, storage for decay, then again we get rid of it. But then this waste, characterization, segregation, then these streams, and then you see here the generic road maps. So this map can be used as a generic road map and then adapted depending on what kind of processing technologies are available in a certain center that deals with radioactive waste. So if nothing it is there, then you will look to the simplest possibilities that you have. Maybe you are lucky and can have the storage for decay. Otherwise, you will look to the potential possibility to develop something and then to add into the roadmap and properly deal with radioactive waste management in your country. For this use, sealed radioactive sources, the management steps are different from this generic. And you see here that you see this use source. You are trying, maybe you can get rid of it, returning to the supplier. So very often the sealed radioactive sources are purchased from abroad. So in many countries, these sources are purchased from some organizations that are located in Russian Federation, United Kingdom, in Canada, in South Africa. They produce sources, and currently the generic policy is that in the initial purchasing contract you put a claim that after the usage you'll return back to the producer, and that's it. You get rid of this future big problem what to do with radioactive waste in the future when the source will become disused. If not, then you are looking leaking, non-leaking, and then you see here very short-lived, and long-lived, and the approach are different. So if it is long-lived, then intermediate or deep disposals, deep geological disposal like high-level waste, what to do. If it is short-lived, you can go to near-surface disposal, and if it's very short-lived, landfill disposal. So now we look to the main processing and storage activities. So here we have sorting and segregation, treatment, conditioning, and then storage. And here some examples of these processing and storage activities. So we speak about pre-disposal. So that means combination of two words: preliminary disposal, something which is done doing before disposal, pre-disposal. So it's not yet disposal. This is all. So any waste management, all waste management activities carried out prior to disposal. Of course, that if it is possible, delay decay is an approach. If not, then we concentrate and contain. And sometimes, if the amount of the waste is very small, and we have the possibility to dilute, let's say, some liquids, then we can dilute and disperse. We will be below the clearance levels, and the regulator will allow us to dilute and disperse, so to do the discharge. So you see here schematically, characterization again is everywhere. Everywhere we have characterization. Extremely important to be an expert in characterization. You will be needed everywhere in nuclear industry, absolutely everywhere, starting from generation of the waste, from medical, from research and so on, and ending with the disposal, everywhere. So pre-treatment, treatment, conditioning, storage, and disposal. So waste characterization, it is important. Everywhere you had a preliminary lecture, 1.5 hours or how long it was there, by Peter Matveyev, where you saw that. So that are taken some pictures from radioactive waste management organizations, where automatic control it is done to scan the drums and to identify what is there inside. Then pre-treatment. So that's any or all operations to get the waste ready for treatment, for real treatment. And here, pre-treatment is collection, when we collect from producers, segregate into the streams. Sometimes we need to do size reduction if the piece is too big in size, or if it is liquid, to adjust chemically, maybe it's too acidic or too basic solution, so it's corroding, is making troubles and keeping this waste, dealing with this waste. Then we do chemical adjustment, so we correct the pH, let's say. And decontamination, dear colleagues, decontamination is considered as a pre-treatment technology. That's the definition that was adopted everywhere. And we are happy or not, decontamination is pre-treatment, not real treatment. So collection, we put in the bins, we segregate into the streams using some glove box. So these are that we separated large pieces and small pieces. The main objective is segregate the waste into active, non-active streams, or higher activity, lower activity, separate an active stream into components, convert the waste into a form that it may be easier than treated conditions and packed, and recover products for recycling. So the result of pretreatment, we have improved safety, lower radiation exposure, lower costs, and subsequent waste management operations, and we are looking to balance, not to pay too much for this pretreatment. So everything should be balanced. And decontamination is a part of pretreatment, where we are trying to reuse some items, some good equipment, we just decontaminate them and reuse them, some parts of the equipment and so on. Or by decontamination, we can reduce and move the class of waste from, let's say, intermediate level waste to low level waste, or maybe low level waste to exempt. So if something that is very deeply contaminated, remove contamination, and the big bulk of material is exempt waste, non-radioactive, and we are doing something very useful. Minimize exposure of personnel. So then again, we need to balance things that we do with that. We move after that, after the pretreatment, to real treatment, because real treatment does three things. The first one is reducing the volume. It's very expensive in radioactive waste management to deal with the large volumes. The larger is the volume, the larger is the cost. If you go to the whole cycle and to the disposal, then the cubic meter to be disposed of into a geological repository can be over €1 million per cubic meter. You imagine that it is huge amounts of resources. So we are interested to make this 1 cubic meter into 1 liter just. So 1,000 saving. It is a lot. So volume reduction is extremely important. Activity removal. So by treatment, we can remove the activity from huge volumes of contaminated water, obtain some sludge, which are 100 times smaller by the volume, and the activity is removed from the bulk of the water and is concentrated just into the sludge. Or change of composition. So let's say we have a pile of burnable, some rags, some clothes which are radioactive, and they can catch fire. And if they caught fire, then there's a very huge danger to the environment by the emission of everything which is burning. So we change the composition. We oxidize these materials into an incinerator. We produce oxides, and these oxides are then non-incinerable and non-burnable. So we change the composition of the material. So colleagues, please be quiet. For the selection of the treatment process, there are guidance documents. The last one published by the IAEA, it is this technical publication number 1817. So it's on selection of technical solutions. So you can use it, download and use it as a guidance. There is for a gaseous waste another also very good guidance published by the agency. so-called handbook is for treatment of radioactive gaseous waste. So you see here the number of this document again can be taken. Then after the treatment, let's say after incineration, we have got some ashes. So we need further to condition these ashes. After the treatment of liquids, we got some sludges. We need to condition the sludges. So there is a separate activity is called condition, or after cutting, after pre-treatment of big pieces, we produce some small pieces. We need to condition them. So these are operations that produce a waste package which is suitable for handling, transport, storage, and or disposal. So in conditioning, we have immobilization, because if we speak about the sludges, the radionuclides are still mobile. They can dissolve back into the water. We need to immobilize them. Packaging, we need to put these pieces of, let's say, some solid material, these ashes, let's say, into a package. So we are doing packaging. Or can be even overpacking. We can have some small packages or some not reliable packages, small packages, use some drums. They are used just for collecting of the waste and interim storage. The walls are thin. We cannot use them for disposal or for long-term storage. Then we will use overpacking. We'll put these drums into a bigger concrete-made container and then safely store this waste or safely transport or safely dispose of. So that's conditioning and the definition of conditioning. So again, immobilization, it's a part of conditioning process, can be a part of conditioning process, where we convert the waste into waste form, which reduces the potential for migration, dispersion of radionuclides during handling, transport, storage, and or disposal. And we do that by solidification. If we have this sludge, it is not solid, we solidify it, let's say, using cement. We can embed the materials into again, grout. Or encapsulation, when we can encapsulate in glass composite materials the ashes. So the ash particles are surrounded by the glass matrix, and then everything is encapsulated into the body of the glass. About the matrix materials, there are guidance materials. One of these is this book, Materials for Nuclear Waste Immobilization, which I published together with Professor Neil Hyatt, which worked long time in mobilization science laboratory in Sheffield. Now he moved to the main organization of United Kingdom dealing with radioactive waste as scientific advisor, Professor Hyatt. So there are details there. So we have cements, bitumen, polymers, glasses, ceramics, and detailed information can be found in these guidance documents. So I have a little time to speak about, but the generic guidance, it is in this slide. So look here, this is classification of radioactive waste. Half-life, it is going in this direction. This is 30 years, so here long-lived and here short-lived. And here activity is going higher and higher. And on the top, we have high-level waste that need to be disposed of in geological facilities. Then guidance is to use glasses, ceramics, metal containers. If we decrease the activity and there is no enough heat generation, the activity is not so high like in high-level waste, again we have glasses, bitumen, cements, geopolymers, high-integrity containers, concrete and metal containers. If we speak about this 96% of the waste in the world, the bulk, almost all the waste generated is low-level waste, then cement is the main material. Can be bitumen, polymers, geopolymers, high-integrity containers, concrete and metal containers. And for low-level waste, typically there is no need to use matrix material because there is not high hazard. They are very close to the exemption levels where indeed this waste is said it's non-radioactive, is exempt, although has some small amount of radioactivity there. So packaging and overpacking, different type of containers are used. So starting from this very simple, typically 200 drums are used by the nuclear industry. Can be used ISO containers, concrete containers of different shape, larger, smaller in volume, so can be big boxes, 10 cubic meters, even how larger can be. It depends if we are speaking about the commissioning waste, then huge. So that's not radiopharmaceutical waste. So we prepared the waste for storage and future disposal, transportation. So storage first. Storage is the temporary holding of radioactive waste. The definition is given here. in a facility that provides for their containment with the intention of retrieval. So storage is not disposal. The license for a storage facility is issued for a certain period of time. And it is warranted that after this storage time, it is safe to retrieve the package from there, and it's still transportable. It's still all the activities inside. There is no holes into the containers and so on and so on. So that differs from the disposal. The storage can be for 10 years, 5 years, 10 years, can be shorter, of course, can be even 100 years, can be even longer. So that's the case, let's say, of North Holland. So they are using the long-term storage over 100 years. So the licenses for so time. United Kingdom also has approved the very long-term storage of the waste beyond 100 years. But please take into account that if we speak about such long times, because of retrieval at the end, because we should care about the integrity of containers, they become, these facilities operation, extremely expensive. So the air which is there inside is conditioned. So let's say in North Holland, even some art objects are kept there because the environment is so safe and good inside that there is no any aging there of some artifacts that should be otherwise maintained in a refrigerator in somewhere in a very controlled atmosphere and so on and so on. And they be kept together, not together, of course, nearby, but in the same big facility with this radioactive waste, which provides inside very good conditions for the storage. Constant temperature, controlled atmosphere, no variations, all these things. That costs. You need to pay for that. Okay, so I'm getting to the end, which the end of our story in radioactive waste management is the disposal. So everything that we do is to prevent, to avoid the generation of radioactive waste, to minimize the generation. If we generated some radioactive waste, it's good to prepare it for reuse if only possible, to recycle some materials if only possible, other recovery to do if it is only possible. So in this direction, it is increasing strategic preference. So the most preferred, preferred approach, it is avoidance prevention. Into this direction is increasing environmental impact. And if no way to get rid of radioactive waste, to recycle and so on, we have to use disposal. So the definition of disposal is given here. So that's emplacement of the waste in an appropriate facility without the intention of retrieval. And in order to ensure that it's safe to do so, we have the waste, and then we have a number of barriers around it. So first we have, so the schematic, it is, don't take that physically it is done, namely exactly. It's similar, but not exactly. So we have engineered barrier systems. So let's say we have waste form, where the material is embedded, container, some additional materials that serve as barriers. Then we have the natural biological barrier, geological barrier. So that's the rock where we emplace the radioactive waste, and then only after that we have the biosphere. So we ensure that during geological time, for high level waste, long lived waste, the impact of this waste to biosphere, it's minimized. What are the main sources recommended? Again, for selection is this recent document published by the agency. About 2002 and 2003, the agency published two scientific and technical bases for the near surface disposal and for geological disposal. You can download these documents, and a month ago, like that, with Professor Steinmetz from the University of Aachen, he published, so that link is operational. This is a open access publication on currently used approach on disposal of nuclear waste in the journal Energy. So that for the details, you can get there and get more than just this, my few words about that. So that's a table about different approach in the disposal. So here we have near surface disposal facilities that can be without engineered barrier system, can be with barrier system. we have got borehole type of the disposal. And then geological disposal with their features and their limitations. And you can imagine that if you go to the deep disposal, we need to pay much more than for near surface disposal. For the borehole disposal, which looks to be much cheaper, several cheaper compared with geological disposal in shafts. And the question is about hundreds of millions of euros, of dollars for such facilities. So if you say 2 times we decrease the cost, overall cost, then that's the question of many millions of so that's huge amounts. So the last achievements, recent achievements, which were overviewed in an overview, of which I'm a co-author, it is the boreholes which on achieving a suitable geological formations turn, and then we have a horizontal borehole, which is just a continuation of a vertical borehole, and the waste can be then in place. Let's say we have a good layer. In many countries, there are such good layers of clay, which is a fantastic good place for the disposal of hazardous waste, radioactive waste. Then we can stay in this layer by using this approach. Can be, by the way, a layer of salt, and salt is a water-soluble material. But if the salt it is there in geological times, it means that the water never comes there for millions and millions, and we know that from geology, hundreds of millions of the years. So we can put there our stuff and be sure that the next 100 million years, nothing will happen there that can compromise the disposal there. So we planned even to have a joint United Kingdom Russian workshop, because this approach is interesting for whole disposal for many experts in United States, in United Kingdom, in Russian Federation. We planned it for the summertime of this year, but due to the events that happened now in Europe here, it was cancelled, and I don't know whether it will occur or not. So nevertheless, University of Sheffield and the Institute of or Deposits of Russian Academy of Science plan to have a more detailed discussion. So here is the summary. Because I'm getting to the end, it's here indication that it is based on IAEA. And here it's for the waste class, the treatment option, conditional option, and endpoint. And here you see I'm going through the classes of radioactive waste, starting with a very short-lived, solid and liquid. Then we go to very low level, then to low level, solid and liquid, then intermediate level, solid and liquid, then high level solid, if you speak about some sealed radioactive sources, can be spent nuclear fuel, high level liquid. And dear colleagues, I finish here my lecture exactly almost a minute by time. And if there is still a minute for questions, then please. If not, then thank you for your attention. So let me somehow that everything went fine. Can you still hear me?
Yeah.
Спасибо, Михаил Иванович. Все, да? Лекция закончилась, да?
Да, все закончилось. Спасибо за внимание. Надеюсь, еще увидимся.
Всего доброго.
Всего доброго. All the best, colleagues. I believe in. I hope that we will meet each other in other places later. Bye.
Можете отдохнуть, попить чай, сейчас у вас... Сейчас где Да, я просто закрываю, да, конференцию завершила. Ага.